Okay, where I wanted to start with this week's video lecture is backing up just a little bit from where we left off in person on Tuesday. And sorry, that is to talk about the concept of measurements. Measurement is a process of finding the magnitude of something, but measurement always requires some kind of device for measuring, like a ruler or a measuring cup or a scale or something like that. You can also find the magnitude of something by counting individual items. You could find the magnitude of the size of your rock collection by counting the rocks in it. Or you can, for instance, count how many pencils there are here on this paper just by going 1, 2, 3. And you don't need any kind of measuring device in order to do that because you're counting individual items. The nice thing about being able to determine a magnitude by counting items is that it gives you an exact number. There's no error involved in this. There are 3 pencils right here, no more, no less, not 3.5, not 2.99. It's 3 exactly. You could write that if you wanted as 3.00 with zeros continuing on to an infinity because it is exactly 3. So when you count individual items, like the pencils here on the paper, or say like the number of eggs in a carton, or something like that, you get an exact number with no error associated with it. Other quantities require measurements or calculations in order to quantify them. And that gives you a number that does actually have some error or some rounding in it. When you take, for instance, a ruler, I don't know how well you can see that, but if I draw a line on the piece of paper here and I say I want to measure how long that line is, I need to, first of all, to use a ruler because my eyes aren't marked off in centimeters or inches for that matter. And so you need something to help you gauge the size of it. The process of measurement usually involves comparing an item or an object or a sample to some agreed upon standard. In this case, the agreed upon standard that I'm comparing the length of this line to is centimeters or millimeters, depending on how you want to look at it. And I can tell the length of the line by comparing it to the markings for the millimeters or the centimeters on the ruler. And you can see here that it's a little bit more than 1.5 centimeters. There's 1 centimeter right there. There's 1.5. It's a little bit past that. So if I call this, sorry, if I call this 1.5 centimeters, then obviously that number is very rounded off, and there's quite a bit of error associated with that. If I wanted to read it more accurately, I could look at the millimeter markings, and I can see that I need my better reading glasses in order to see that. There's one thing I can see. All right, so starting at 0, we have 1.5, 1.6, 1.7. Looks like not quite 1.7. So I'm going to call it maybe 1.69. And the standard procedure in science for measuring things is that you read the measuring device to the smallest markings. The smallest markings in this case would be millimeters, and that is known as the least count of the measuring device, the smallest markings. And if possible, you try to estimate how far it is between the individual markings. And that will be your last digit. So you read to the smallest markings and estimate 1 digit beyond that. In this case, the smallest marking would be 1.7, but if you look really closely, it's a little bit short of the line for 1.7. And so that's why I'm saying it's 1.69. That's a judgment call, as I mentioned in class the other day. We assume that when we do a measurement properly, like I just did, that we assume that the last digit is uncertain to a degree of plus or minus 1. So if you looked at that and said it looks more like 1.70, I'd say, okay, that's a reasonable number. And if you think it looks more like 1.68, I'd say, okay, that's a reasonable number too. So I labeled it as 1.69 with the understanding that it could be anywhere between 1.68 and 1.70. And that means that there's a certain amount of error involved in that measurement. No matter how careful I was, I'm not going to be able to get the absolute final definitive length of that line. There's always going to be at least a little bit of error involved. Some of the error involved involves the sharpness of my eyesight, which leaves something to be desired in close-up work, as evidenced by the fact that I had to put on better reading glasses to read the ruler. And it has to do with, say, the thickness of the individual markings on the ruler. It has to do with the accuracy of the markings on the ruler. We're taking it on faith that the guy who made the ruler knew what he was doing and put the markings the right distance apart, but that may not be the case. And also there are outside conditions that can affect it too, like temperature. Things expand a little bit when they get warm, they contract a little bit when they cool down. So expansion or contraction can affect how far apart those markings are too. It wouldn't have much of an effect in this case, but some. And if you were measuring something that was really long, it could have a significant effect in that case. Some of the examples of things that require measurement rather than counting would be, for instance, masses, if you want to know the mass of a sample, or length or width or height, like the length of that line, that's just off screen, or volume, say a volume of water. You can use a graduated cylinder. And as I mentioned in lab, graduated cylinders are tall and skinny, which means that they're pretty accurate for measuring volumes, but there is still going to be some error. And for that matter, the number of molecules or atoms in a sample. Because atoms are so small, and molecules too are so small, that we cannot see individual atoms or molecules, there is no way for us to count them directly. There are ways, though, that we can calculate the number of atoms or molecules in a sample, and we'll get to that later on. But anyway, since it involves measurement, like for instance, finding the mass of the sample, and then calculations involving some of the numbers from the periodic table, that means that there will be some error in it. So anything that you cannot count directly will have some error in it. As I said, measurement is a comparison of a quantity to a known standard, a known and universally accepted standard. For instance, that line versus the standard of centimeters, or your height versus the standard of inches, or your weight against the standard, the accepted standard of the pound, and so on. Measurement conveys, and also obviously with measurements, the measurement in most cases does not come out to be a whole number. So you'll have a whole number, and then you'll have a fraction of a unit beyond the last whole number. So like, for instance, I'm about 5'10" in height. So that would be 5 complete feet, and then 10/12 or 5/6, I guess, of a foot beyond that. Measurement conveys 3 types of information. First of all, there's the magnitude, which is the number. And then there's the standard for comparison, which is the unit. So in this case, the magnitude is 1.69, and the unit is centimeters. And keep in mind that with a measurement, neither one of those things means very much without the other one. I could draw that little line there and say the length is 1.69. And if I didn't specify that I'm talking about centimeters, if you're not really that familiar and haven't used rulers a lot, you might think I'm talking about inches. It's actually quite a bit less than 1.69 inches, but you might not know. You might not be that familiar with it. There are other units too that have been used over the years that I might be talking about. So the number doesn't give you much information. And at the same time, I could say the length is centimeters. And that doesn't tell you really anything, because any length can be measured in centimeters. You need the number and the unit together to tell you what size something is. And also there's some uncertainty. Again, anytime you do a measurement, there's some uncertainty because of error and or rounding off of numbers. When you do a calculation, very often your calculator will spew out 10 or 12 digits. And most of those digits are just fantasy in the calculator's tiny little brain, and they're not real. And we will come a little bit later to a method for determining which of those digits are real and should be written down and which of them are not real and should be ignored. The uncertainty is not always explicit. Like you could make the uncertainty in this measurement here explicit by saying 1.69 centimeters plus or minus 0.01 centimeters, because we estimated the last digit. It's the second digit past the decimal point. So that would mean, again, it could be as low as 1.68, which is what you would get if you subtracted 0.01 centimeters, or it could be high as 1.70, which would be what you get if you add 0.01 centimeters to 1.69. That's one way of conveying error explicitly, but in most cases, we don't convey it explicitly. So you have to have kind of an idea based on other factors how much error there's likely to be in a measurement. Okay, the parts of the measurement. The number can be written in either decimal. Let me get that on screen. The number part of the measurement can be written either in decimal form or scientific notation, or a kind of hybrid form that's not really fully one or the other. Appendix B in our textbook has a review of scientific notation and how to do it. And also I wrote myself a note here because I like the way the old textbook presented this kind of information. So I am going to, as soon as I find some paper, I am going to get into scientific notation the way it was done in the old book. Okay, scientific notation. Scientific notation is useful for very large. Okay, I've got 1,000 pens around here and I can't find one that works. Okay, scientific notation is good for very large or small numbers. As I mentioned, for instance, size of an atom is 0.0000000001 approximately meter. And that is a really small number. It would help if we could write that in a much more convenient sort of way that would convey its magnitude without us having to count all those zeros. Well, in scientific notation, it's just 10 to the minus 10 power. And that's obviously a lot easier. It's a lot more compact. You don't have to write all those zeros, and you don't have to sit here and count all those zeros either. It's even more compact to write it as 1 angstrom, but the angstrom is not that important a unit, so I'll just throw that in there. I mentioned the angstrom during class on Tuesday. And again, if you have half an ounce of, a little less than half an ounce, 12 grams of carbon, the number of carbon atoms would be approximately that. That's 602 followed by 21 zeros. That is an extremely large number. And because we have to deal with quantities that are often much smaller or much larger than we're used to dealing with in everyday life. That's why we need something like scientific notation to give us a convenient way to represent very large or very small numbers conveniently, in a way that we can sort of get an idea of what the magnitude of the number is without having to count a lot of zeros. In scientific notation, that number is just 6.02 times 10 to the 23rd power. And that is, much more compact, obviously, and you don't have to count all those zeros. There are two parts in scientific notation: the decimal and the exponent. The decimal is a number between 1 and 10. And notice the way I wrote this up here: 6.02 times 10 to the 23rd. 6.02 is between 1 and 10. I could have written this as 60.2 times 10 to the 22nd, but that would not be proper scientific notation because 60.2 is not between 1 and 10. So the decimal part of the number has to be between 1 and 10. And the exponent part is just 10 raised to a whole number power. That the exponent is the power that 10 is raised to. If that does need to be a whole number for it to be proper scientific notation. It is possible to raise 10 to a power that's not a whole number. And if you want to know what that is, you can always just go to your calculator. For example, if you want 10 raised to the 3.5 power, you can just enter that in as 10 caret 3.5. The caret is meaning raise it to this power and hit equals. And we get 3,162.27766. Okay, but for scientific notation, that power has to be a whole number. Okay, so the usual form of scientific notation is going to be a number between 1 and 10 times 10 raised to a number raised to a whole number power. Okay, so it's like this. This number up here that I wrote is 10 to the minus 10 meters. In proper scientific notation, that would be 1 times 10 to the minus 10. But because 1 doesn't actually change the value any, I left it out. But notice you got a number here that's between 1 and 10. Well, it is 1, but that's okay. Okay, so in order to convert from, say, scientific notation to decimal form or the other way around, first we need to look at what the exponential part means. If the exponent, that is, if the power of 10 is positive, what it means is 10 multiplied by itself that number of times. Okay, so for example, 10 to the first power is just 10. 10 to the second power is 10 times 10. That is, you write down 10 twice and multiply them together. And that, of course, is 100. 10 to the third is 10 times 10 times 10. And when you work that out, that's 1,000. And so on. I didn't say anything about what if it's 10 to the 0 power, because that's a definition in mathematics. Anything to the 0 power is 1. Doesn't matter what it is. It could be 10 to the 0 power, that's 1. It could be 10 billion to the 0 power, and that's still 1. So that's always true. If the power of 10 is negative, what that means is 1/10 multiplied by itself. That number of times. So 10 to the minus 1 would be equal to 1/10, or in decimal form, 0.1. 10 to the minus 2 would be 1/10 times 1/10 equals 1/100th, or 0.01. 10 to the minus 3 would be 1/10 times 1/10 times 1/10, which is 1/1000th, which is 0.001 in decimal form. In order to convert decimal to scientific notation, the best thing to do is move the decimal point until the number is between 1 and 10. Okay. And let's see, count up the number of, then you multiply it by 10 raised to the power of the number of spaces the decimal moved. And an easy way to remember whether the power should be positive or negative is, well, first of all, just keep in mind that basically large numbers have positive powers and small numbers have negative powers. So, and the dividing line is 1, because 10 to the 0 power is 1. So if the number is smaller than 1 when you start out trying to convert it to scientific notation, then it's going to end up with a negative power. And if the number is greater than 1, it's going to end up with a positive power. But also, you can reason it out if you forget that. And that is, if moving the decimal makes the number smaller, the power is positive. Because when you're converting a number from decimal form to scientific notation, you're not trying to change the value of the number. You're just trying to express it in a different way. And so if you make a change by moving the decimal point that has an effect on the magnitude of the number, you have to compensate for that by giving the sign of the exponent the right positive or negative. So if moving the decimal point makes the number smaller, you need to compensate for that by making the exponent bigger, in other words, positive. And if moving the decimal makes the number bigger, then the power of 10 would be negative. You're not trying to change the value again. So if you make a change by moving the decimal that makes the number bigger, you have to compensate for that by making the exponent smaller, by making it negative. Okay. Looking at some examples, we could say 96,485. If you if you have that number in decimal form, and you want to change it to scientific notation, again, what you do is you move the decimal point until the number is between 1 and 10. In this case, we obviously have to move the decimal point to the left because moving it to the right makes the number bigger. 96,485 is way more than 10. So we can move it one space and we get 9,648.5. That's still not between 1 and 10, but it's getting closer. It's getting smaller. We could move it one more place. We have 964.85. That's still not between 1 and 10, so move it again. 96.485, still not between 1 and 10, but it's getting closer. Try it once more. 9.6485. That is between 1 and 10. It's a little less than 10, so that's within the range we need. So that's the decimal part of the number. 9.6485. And that's going to be multiplied by 10, raised to the power of the number of spaces we move the decimal, 1, 2, 3, 4. And is that going to be a positive 4 or a negative 4? Well, 96,485 is bigger than 1, so we can tell right away it's going to be a positive 4. But also notice that when you move the decimal point, you made the number smaller. If we went from 96,485 to 9.6485, which is a lot smaller. So that means the exponent has to be bigger, or in other words, positive. The reason that that works out is you can look at doing this step by step if you want to. Start out with 96,485. If you wanted to express that in a form that kind of looks like scientific notation, but isn't proper scientific notation, you could write this as 96,485 times 10 to the 0. Because 10 to the 0 is 1, and you can multiply anything by 1 without changing its value. So 96,485 is the same as 96,485 times 10 to the 0. We just don't write 10 to the 0 because, it doesn't change anything. There's no point. It's just a lot of extra work. If you move the decimal point one place to the left, you then end up with 9648.5, and that would be 9648.5. And moving the decimal point made the number smaller, so you have to make the power of 10 bigger. So 9,648.5 times 10 to the plus 1 is the same thing as 96,485. If you then move that decimal point one more time, you get 964.85. And you could write that as 964.85 times 10. Now, moving the decimal point again made the number smaller again. So the exponent has to get bigger again to compensate. So 964.85 times 10 to the plus 2 power is the same as 96,485. We wouldn't want to stop here because this is not proper scientific notation, because that first part of the number is not between 1 and 10 yet. So we move the decimal point again. 96.485 would be, or in scientific notation, that would lead us to 96.485 times 10. Now moving the decimal point again made the number smaller, so we want to make the exponent bigger again to compensate. 96.485 times 10 to the third is the same as 96,485. And once more, and we get 9.6485. Finally, we have a number that's between 1 and 10 to start this off. And we were at 10 to the plus 3, so we made the number smaller again by moving the decimal point, so that has to be 10 to the plus 4 now. And so all of these numbers on the right-hand side here have the same value or the same magnitude. It's just that only the final one is proper scientific notation because of the requirement that the first part of the number be between 1 and 10 And then you can multiply that by 10 raised to a whole number power. Sorry. We could look at a few other examples here. If we want a smaller number, say 0.00365, if you want to turn that into scientific notation, we need to move the decimal point again in a direction that will give us a number that's between 1 and 10. So we move it to the right this time, and we move it one space to the right, and we have 0.0365. That's still less than 1. Move it one more. How about 0.365? That's still less than 1. So how about 3.65? Bingo. Now we're there. That's a number that's between 1 and 10. And so it's going to be 3.65 times 10 raised to the power of the number of spaces we move the decimal, 1, 2, 3. And because this started off as a small number, a number smaller than 1, it's going to be -3. But also notice that when we move the decimal point, we made the number bigger. And so we have to compensate for that by making the exponent smaller or negative. Okay. So here are a couple of examples that I'll give you, and you can stop the video for a moment and see if you can get it in scientific notation on your own, and then we'll come back together and see if we can, see if you got it right. Okay, 186.5. Okay, stop the video, try it, and then start the video again. And okay, if you're coming back and you've started the video up again, 186.5 is a number that has a decimal point in it already. So you just move the decimal point in whichever direction makes the number between 1 and 10, and you end up having to move it 2 places to the left. 1.865. And that's going to be times 10 raised to the second power, because we moved the decimal point 2 spaces to get this number to be between 1 and 10. And in doing so, we made the number smaller, so we have to make it a +2 as the exponent. And of course, 186.5 is bigger than 1. So you might have noticed from the very beginning, then it should be a positive exponent. I've been writing in the plus sign explicitly here just to make it clear, whether it's positive or negative. But of course, with positive numbers, you generally don't have to write the plus if it's a positive number. So you could have written just 1.865 times 10 to the second, and that would be fine. Okay, 0.0. Okay, so how about 0.000947? And okay, you can stop the video for a moment and see if you can get it, and then we'll come back. Okay, if you're coming back now, hopefully you've got something for this. 9.47 is going to be our number that's between 1 and 10, because we have to move the decimal point 1, 2, 3, 4 spaces to the right, which gives us 9.47. And it's going to be times 10 raised to the power of 1, 2, 3, 4. And since the number we started off with was less than 1, that's going to be -4. And also because moving the decimal point made the number bigger, you have to make the exponent smaller to compensate. So that reinforces that it's -4. And hopefully that will sort of get the point across. Okay, converting scientific notation to decimal is essentially the reverse of what we just did. But I see I'm over time for the first segment of the video, so I'll stop there and we'll come back in a moment with segment B.